In this video, we are going to see about the equivalent circuit. So when the alternator is under no load, there is no flow of current in the armature conductors. Only EMF is developed. Okay, but when an alternator under load, the current is flowing through the armature conductors. Okay, whenever a current is flowing through the resistance, there will be a voltage drop. Similarly, reactance also. So when an alternator under load, there will be a three voltage drop occurs. So the first voltage drop due to the armature resistance, second is like armature leakage reaction, third is armature reaction. Okay, we'll see one by one. So the armature resistance is nothing but the resistance of an armature conductor. Okay, when a current armature current IA is flow through the armature, then the IA into RA will be the voltage. That means the IA RA voltage drop will occur in the armature. The second thing is like leakage reactance. When current flow through an armature winding, the flux is set up here, but the 100% of the flux will not be utilized. Only the part of it does not cross the air gap. So usually the flux set up at the air gap, so the part of flux will not cross the air gaps and links the coil sides. Okay, so this leakage flux alternates with the current, so this gives a winding. We call it a self inductance. This is called armature leakage reactance. Okay, so therefore the current flow through the when the current is flowing, then the IAXL, that is a armature leakage reactance, voltage drop will be occur. Okay, so this also effective in reducing the terminal voltage. The third one, as we discussed in the previous video, the armature reaction. The armature reaction provides the cross magnetizing and demagnetizing and magnetizing efforts based on its power factor. Okay, generally the loads are inductive in nature, so most cases we don't use the capacitive loads. So generally inductive or resistive loads. So the load will under unity or lagging power factor, so there will be considerable armature reaction, so that results in a voltage drop in the circuit. Okay, so that also will reduce the voltage of the terminal. So this also we call it as an voltage drop due to the armature reaction. So why do we call it as the voltage drop? And if you notice here, the armature will have an effect, that is a cross magnetism or demagnetizing. So when the demagnetizing happens or cross magnetism happens, there will be distortion in the waveform when it is a cross magnetizing. When it is a demagnetizing, the flux will be reducing, so that the voltage also reducing, so there is a voltage drop at the terminal. Okay, so these three are important drops in the alternator. So we'll see the equivalent circuit now. Okay, you can see the E phase, that is nothing but a EMF generated, that is the no load voltage or no load EMF, and XAR is nothing but a armature reaction resistance, armature reactance, and XL is a leakage reactance, RA is the resistance of the armature. Okay, when the current flow through the armature current, that means IA flow through this thing, there will be a drop, as I told. So the E phase, that means E phase equal to E phase dash, that is nothing but after armature reaction voltage drop. Okay, that E phase dash equal to Vt, that means the terminal voltage, that is the N terminal voltage, plus Ia into Ra plus JXL. So this Ra is nothing but armature reactance, and XL is nothing armature resistance, and XL is nothing but a armature reactance. So there will be a drop that we call it as Z. Okay, so the drop plus the voltage terminal, so if adding together, then we can get the E dash phase, that is after the armature reaction. So if I ought to include the armature reaction, then the no load EMF equal to E phase equal to E dash phase plus Ia into the, that is Ia is nothing but armature current, plus J into XAR, that is XAR is nothing but armature reactance resistance. Okay, so the equivalent circuit, if I reduce it, the XAR plus XL is nothing but a XS, that is a synchronous reactance. So only the resistance Ra, and the other two reactance is nothing but XAR plus XL. Okay, so I combine together so that the total reactance, that is impedance, will be ZS. Okay, so now we'll see about the synchronous reactance. As you know that the synchronous reactance is a fictitious reactance that is employed to account for a voltage effect. That means the voltage effect, in this case it is a reduction of voltage. Okay, so in an armature circuit, an actual armature leakage reactance plus change in the agar flux caused by the armature reaction. Okay, so the voltage drop occurs due to that. So the synchronous impedance here is nothing but the combination of two reactants. The reactants, one is leakage reactance and second one is armature reactance. So it is account for voltage drop. Okay, so that is why we have to include this. So the XS equal to XL plus XAR. So the total impedance, that means synchronous impedance, will be Ra plus JXS. So the total phase voltage, that means no load EMF equal to terminal voltage plus total drop, that is Ia into Zs, and that is equal to V terminals, the same VTH, it is wrong, it is VT only, and Vt plus Ia into Ra plus JXS. Here you have to notice here, this is Vt only. Okay, so this combining together is provide the equivalent circuit. The equivalent circuit contains armature resistance plus synchronous reactance. So both we call it as the total, we call it as vector sum, we call it as a impedance of the circuit. Okay, thank you.